After studying this module, students, you shall be able to understand the position, intensity and shape of absorption bands related to various functional groups. Understand how mesomeric and inductive effect change the absorption frequency of carbonyl compounds. Understand ring strain effect on various ring systems, cyclic ketones, lactams, lactones, etc. And you will also understand how to differentiate primary, secondary and tertiary amines on the basis of IR spectroscopy. Let us now begin with the introduction of this topic. The infrared spectrum of an organic compound contains a large number of bands due to the stretching and bending vibrational modes of each bond involved in that molecule. Now, this is quite difficult to assign each and every band to a particular mode of vibration. Then, organic chemists generally do not try to identify all the absorption bands in an IR spectrum. The organic chemists just look at some characteristic bands that you will be dealing with in the present molecule, and then we will learn how to characterize a particular functional group according to those very characteristic bands. Now students, these characteristic peaks tell about the presence of some particular functional groups present in the molecule. Now as more energy is needed to stretch a bond than to bend it, absorption bands for stretching vibrations are found at higher frequency regions, that is functional group region, whereas the absorption bands for bending vibrations are typically found in the fingerprint region. Stretching vibrations, therefore useful vibrations in determining the functionality present in a molecule. The IR stretching frequencies associated with different type of bonds are discussed separately in each different section of this module. Thus, the vibrational frequencies provide important structural information about a compound, and since two same types of bonds in two different type of compounds would vibrate at different frequencies, thus no two compounds can have exactly the same infrared spectrum, especially in the fingerprint region except enantiomers. This makes infrared spectroscopy a simple and a very versatile tool for identification of many organic samples. Now here we describe, students, the various vibrational modes and their characteristic absorption frequencies. First, we now come on to alkyl and aryl halides. It is difficult to determine the presence or the absence of a halogen in a compound by infrared spectroscopy. The Cx, where X is a halogen, absorption bands occur at very low frequencies to the extreme right hand side of the spectrum, that is the fingerprint region, where a number of other bands also appear. Now students, in the table we have listed the absorption regions observed for organic halogen compounds. Particular care must be taken when fluorine is present in a compound, as the CF stretching bands observed in the region of 1350 to 1100 centimeter inverse are very strong and may obscure any CH bands that might be present. Now you can see in this table various group frequency wave numbers are given for CF, CL, CBr and CI bonds respectively, and their assignment has also been given. We now come on to the stretching frequencies of alcohols and phenols. Alcohols and phenols produce characteristic infrared bands due to OH stretching and CO stretching in the regions 3200 to 3650 centimeter inverse and 1000 to 1260 centimeter inverse. The presence of NH or moisture causes similar results. Now, for alcohol specifically, the broad OH stretching band is centered around 3600 centimeter inverse, while for phenols this band appears 50 to 100 centimeter inverse lower than that of alcohols. But the frequency value is always not much reliable, as the position of OH band is very sensitive to hydrogen bonding. A strong and sharp peak is observed near to 3700 centimeter inverse in gaseous samples or extremely dilute solutions of alcohols. In condensed phases, that means in concentrated phases, bulk liquid, that is the bulk liquid is taken in bulk, the alcohol is taken in bulk, KBr discs, that is even using KBr discs and in using concentrated solutions, etc. That is the meaning of condensed phases. The molecules are associated through hydrogen bonding and cause shifting to lower frequencies and broadening of bands. Now, this can be clearly seen in the two figures where we have shown the infrared spectrum of hexanol and paramethyl phenol. Now, you can see and appreciate the values of stretching frequencies which we have mentioned, and in the next, that is the table, you can see the CO stretching and the OH stretching frequencies for phenol, tertiary, secondary and primary alcohols. Now, the CO stretching in alcohols and phenols occur in the region of 1300 to 1000 centimeter inverse region. Now, we are coming to the details of the table that is drawn. The CO absorption are coupled with the adjacent CC stretching vibrations. Hence, the position of CO can be used to differentiate between primary, that is which occurs at 1050 centimeter inverse, secondary which occurs at around 1100 centimeter inverse, and tertiary which occurs around 1150 centimeter inverse. For alcohols and phenols, it occurs around 1220 centimeter inverse. Now, these compounds also produce OH bending vibrations, but the latter couple with other vibrations and produce complex bands in the fingerprint region. Now, as I told you, all this has been completely listed in table, as you can see. Now, we come on to another functional group, students, that is ethers and epoxides. In the spectra of aliphatic ethers, the most characteristic absorption is a strong band in the region of 1150 to 1000 centimeter inverse because of asymmetric COC stretching, but a band in this region is also observed in the other oxy compounds like alcohols, aldehydes, ketones, acid, etc. Therefore, we consider the possibility that a compound is an ether or an epoxide only if the unknown oxy compound shows no absorption bands in the region of OH stretching, that is 3750 to 3000 centimeter inverse, or carbonyl which shows in the region of 1850 to 1550 centimeter inverse regions. Now, this is clearly shown in the IR spectra of diethyl ether, which is taken as a neat liquid using KBr plates. Now, the conjugation of ether with carbon-carbon double bond or phenyl ring shifts the COC symmetric stretching to 1250 centimeter inverse. The resonance involved in the phenyl ring increases the bond order from single to partial double bond, and so higher the force constant and thus higher the absorption frequency. This has been explained to you in the earlier module when we were discussing about the Hooke's law. Cyclic ethers, they show a CO stretching band over a broad range of 1250 to 900 centimeter inverse. Now this can be clearly seen in the infrared spectrum which is shown here, which belongs to anisole, takes into account the resonance effect of the ethers, which is done as a neat liquid in KBr plates. Let us now come to a broad class of carbonyl compounds and learn about their stretching frequencies. Now students, aldehydes, ketones, carboxylic acids, esters, lactones, acid halides, anhydrides, amides and lactams, they all fall in the range of carbonyl compounds and show a very strong C double bond O stretching band in the region of 1630 to 1870 centimeter inverse. The different frequencies of these functionalities can be explained by the inductive effect, mesomeric effect, hydrogen bonding, field effect, steric effect and ring strain. Now these factors either increase or decrease the stretching frequency of both the aldehydic and ketonic group compared to the normal value of 1715 centimeter inverse, that is 1715 centimeter inverse, which belongs to a saturated aliphatic ketone. Now as you can see in this table, this enlists all the wave numbers belonging to alcohols, phenols, ethers, aldehydes, ketones and esters, carboxylic acids, anhydrides, etc. so that you can in one table compare all the values of the CO bond. Now let us now come specifically to the carbonyl compounds like aldehydes and ketones and study their absorption frequencies. Aliphatic aldehydes show a very strong CO stretching in the region of 1740 to 1725 centimeter inverse. The conjugation of an aldehyde to a C double bond C or a phenyl group lowers the CO stretching by approximately 30 centimeter inverse. Now this effect is clearly seen in benzaldehyde, in which aryl group is attached directly to the carbonyl group and shifts the C double bond O stretching frequency value to 1701 centimeter inverse. Now the aldehyde CH stretching vibrations appear as a pair of weak bands between 2860 to 2800 centimeter inverse and 2760 to 2700 centimeter inverse. The higher CH stretching band, that is which is in the range of 2860 to 2800 centimeter inverse of aldehyde, is often buried under aliphatic CH band. But the lower CH band, that is which is in the range of 2760 to 2700 centimeter inverse, is usually used to distinguish aldehydes from other carbonyl containing compounds. The CH bending vibrations appear between 945 to 780 centimeter inverse. Now looking at the figures, we can see here the infrared spectrum of nonanol, which is an aliphatic aldehyde used as a neat liquid in KBr plates to obtain the spectrum, as well as the IR spectrum of an aromatic aldehyde, that is benzaldehyde, which is again done as a neat liquid in KBr plates. You can clearly see the difference in bands and which band is used to distinguish the aromatic from the aliphatic aldehyde. Now let us come to some facts. The aliphatic acyclic ketones show C double bond O stretching between 1720 to 1700 centimeter inverse, which is shifted to lower frequencies by 20 to 30 centimeter inverse on conjugation with C double bond C or a phenyl ring. The presence of two conjugated groups such as in benzophenone further lowers the C double bond O stretching frequency to a lower value of 1665 centimeter inverse. Now students, we take up cyclic ketones and their vibrational frequency values. The frequency of CO group in cyclic ketones increases with the increase in ring size, as has been discussed before in the factors affecting vibrational frequencies. Ring size is one of the factors. The ring strain shifts the absorption frequency values to higher values. 6-membered rings with carbonyl group, example cyclohexanone, absorbs at normal value, that is at 17-15 centimeter inverse. Decrease in ring size increases the C double bond O stretching frequency. Smaller rings require the use of more P character to make CC bonds for the requisite small angles. This gives more S character to the C double bond O sigma bond and thus results in the strengthening of C double bond O double bond, causing absorption at higher frequency values. Now, as you can see in the figure, we have various ring sizes and the aliphatic ketones and their stretching frequency values. Now, you can see as the ring size decreases, the stretching frequency value increases due to more drastic ring strain. Let us now come to another class of carbonyl compounds, which is carboxylic acids. Carboxylic acid, students, which can be denoted by a general formula RC double bond OOH, exist as dimers except in dilute solutions due to strong intermolecular hydrogen bonding. Now, carboxylic acids show a strong peak in the range of 1730 to 1700 centimeter inverse. This band shifts to lower frequency if in conjugation with a C double bond C bond or a phenyl ring. Now, the OH stretching band is appeared as a very strong broad peak in the region of 3400 to 2500 centimeter inverse range. The very broad nature of this band is attributed to the strong hydrogen bonding present in the dimer. In dilute solutions, the carboxylic acids attain a monomeric structure and the inductive effect of oxygen shifts the C double bond O absorption band to higher values, that is in the range of 1760 to 1730 centimeter inverse than what is observed in the ketones, that is around 1715 centimeter inverse. In addition, students, carboxylic acids show a characteristic CO stretching band near 1240 centimeter inverse and in plane and out of plane OH bending bands at 1430 centimeter inverse and 930 centimeter inverse respectively. These bands are of medium to low intensity. Now, let us now look at this figure which belongs to isobutyric acid, which is done as a neat liquid in KBr plates to obtain the spectrum, and you can see the different spectra from that of ketones. Another carbonyl function group, students, is the esters. Now, let us take up the specific case of esters. In case of esters, two strong peaks are observed. The C double bond O stretching appears in the range of 1750 to 1730 centimeter inverse and the CO stretching absorption band appears in the range of 1300 to 1000 centimeter inverse. If the C double bond O group is conjugated with a C double bond C or a phenyl ring, the CO frequency is shifted to lower frequency due to conjugation. If in an ester CO oxygen bears electron withdrawing groups such as vinyl, phenyl, etc., then the C double bond O stretching is shifted to higher values like 1770 centimeter inverse. This increases the electron withdrawing ability of oxygen, causing increase in carbonyl double bond character, thus an increase in the stretching frequency value. Now, you can clearly see the depiction of these values figure, which shows the infrared spectrum of ethyl butyrate in neat liquid and in KBr plates to obtain the IR spectrum. Now students, let us take up cyclic esters. In cyclic esters, also known as lactones, the C double bond O stretching is shifted to higher frequency with decreasing size. The unstrained 6-membered cyclic esters, that is delta valorolactone, absorbs at the same value as a non-cyclic ester at 1735 cm inverse. Now because of ring strain, gamma butyrolactone and beta butyrolactone show a C double bond O stretching at 1770 cm inverse and 1820 cm inverse respectively. This can be easily shown with the structures drawn in the figure that you can see here. We now come on to the next functional group of the carbonyls, specifically known as amides. The CO stretching frequency in amides appears in the range of 1680 to 1630 cm inverse, that is 20 to 50 cm inverse lower than that of carbonyl stretching frequency of ketones. Now the low frequency of amides is due to strong resonance participation of lone pair of electrons by amide nitrogen that weakens the carbonyl bond. The carbonyl stretching band in IR spectra of amide is called amide 1 band and NH bending is called amide 2 band. In the solid or pure liquid states, primary amides, which are highly hydrogen bonded, exhibit 2 NH stretching bands, one at 3550 cm inverse, that is 3550 cm inverse due to NH asymmetric stretching, and the other one is at 3180 cm inverse due to NH symmetric stretching. In dilute solutions, due to lowering in the degree of hydrogen bonding, the absorption bands shift to higher frequency at 3500 cm inverse and 3400 cm inverse respectively. They also exhibit C double bond O stretching at 1680 to 1660 cm inverse range, which belongs to the amide 1 band, and NH bending at 1650 to 1620 cm inverse range, which belongs to amide 2 band. Now this figure, which belongs to the infrared spectrum of propionamide done in Nujol mol or the KBr plates, here the dots indicate the Nujol, which is a mineral oil, and its absorption bands, and you can clearly see the CO stretching bands and the amide 1 and the amide 2 bands. Now the secondary amides show only one NH stretching band at near 3300 cm inverse, while the carbonyl stretching band, that is the amide 1 band, is observed at 1680 to 1640 cm inverse. The amide 2 band for secondary amides is due to the coupling of NH bending and CN stretching and appears at 1560 to 1530 cm inverse. A weak band, which is an overtone of the amide 2 band, appears at 3100 to 3060 cm inverse. A broad NH wagging band also appears at 750 to 650 cm inverse. Now students, as you can see in the infrared spectrum of N-methyl acetamide, a secondary amide, which is done as a neat liquid in KBr plates to obtain the spectrum, these bands can be easily observed in this IR spectrum. Coming on to tertiary amides. Tertiary amides show C double bond O stretching band in the range of 1680 to 1630 cm inverse, but do not show any NH stretching band. Coming to cyclic amides. The CO stretching frequency is shifted to higher frequency with decreasing ring size. The unstrained 6-membered cyclic amide, that is The delta valorolactam absorbs at 1760 centimeter inverse, whereas the gamma butyrolactam and beta propiolactam shows C double bond O stretching values at 1770 centimeter inverse and 1745 centimeter inverse respectively due to ring strain. Now coming on to the next carbonyl functional group, which is anhydrides. The acid anhydrides show two absorption bands due to carbonyl group in the region of 1840 to 1800 centimeter inverse, which arises due to symmetric stretching, and 1780 to 1740 centimeter inverse, which arises due to asymmetric stretching. Conjugation shifts each of these bands to lower frequencies, about 30 centimeter inverse each. Ring strain moves the absorption to higher frequency. Anhydrides also show a strong and broad CO stretching band in the range of 1300 to 900 centimeter inverse for open chain anhydrides. Now this is clearly seen in the IR spectrum shown in the figure, which belongs to propionic anhydride done in neat liquid with KBr plates, and you can see the various values that I have stated before. Now students, let us consider the specific case of acid chlorides and their stretching frequencies. Aliphatic acid chlorides show very strong band due to carbonyl group in the range of 1810 to 1775 centimeter inverse. The high frequency region in the case of acid chloride is attributed to high electronegativity of chlorine. Conjugation lowers the frequency to 1780 to 1760 centimeter inverse. The CCl stretching vibration occurs at 730 to 550 centimeter inverse. This can be clearly seen in the infrared spectrum of acetyl chloride, which is done as a neat liquid in KBr plates to obtain the IR spectrum. Now we come on to amines. We have finished off with the carbonyl compounds and various functional groups associated with carbonyl groups. Now we come on to the study of amines. The NH stretching frequencies occur in the range of 3500 to 3200 centimeter inverse. Primary, secondary and tertiary, that is in which no hydrogen is attached to nitrogen, amines may be differentiated by using infrared spectra easily. Primary amines, that is denoted by RNH2 generally, show two NH stretching bands in the range of 3500 to 3300 centimeter inverse, whereas secondary amines, which are denoted as R2NH, show only one band in that region because of one NH bond. Since tertiary amines do not have any NH bond, thus they do not show an NH stretch. Now in the table given, we summarize the main infrared bands for amines. Now you can see there are various scissoring, bending, wagging vibrational frequencies, which you can see for primary and secondary and tertiary amines. In neat liquid samples, the NH bands are weaker and sharper than OH bands. Primary NH2 amines show two absorption bands, asymmetric and symmetric, near 3400 and 3300 centimeter inverse. It is not possible to assign the symmetric and asymmetric bands by inspection, but it is assumed that the higher frequency band is due to asymmetric stretching, that is near to 3400 centimeter inverse, whereas the lower frequency band results from a symmetric vibration, that is at 3300 centimeter inverse. In dilute solutions, the two frequencies are shifted to higher values. Aliphatic secondary amines show only one NH stretching band at 3300 centimeter inverse, whereas an aromatic secondary amine gives stronger NH band at 3400 centimeter inverse. Tertiary amines do not show any NH stretching band. This can be seen, which show the infrared spectrum of butylamine, dibutylamine and tributylamine done as neat liquids in KBr plates, and you can see the various stretching frequencies which are there and which are absent in case of primary, secondary and tertiary amines. Now, the NH bending mode, which is the scissoring, appears as a medium to strong intensity broad band in the range of 1640 to 1560 centimeter inverse. In the aromatic secondary amines, the band shifts to a lower frequency and appears near 1500 centimeter inverse. However, in aliphatic secondary amines, the NH bending vibration is very weak and usually is not observed. The NH vibration in aromatic compounds often overlap the aromatic C double bond C ring absorption, which also appears in the region. Sometimes an out of plane NH bending vibration also appears as a broad band in the region of 850 to 750 centimeter inverse from primary and secondary amines. These bands appears in the spectrum of compounds determined as neat liquids and are seen most easily in aliphatic amines. The CN stretching absorption occurs in the region of 1350 to 1000 centimeter inverse as a medium to strong band for all types of amines. Aliphatic amines absorb at 1250 to 1000 centimeter inverse, whereas in the case of aromatic amines they absorb from 1350 to 1250 centimeter inverse. The CN absorption occurs at a higher frequency in aromatic amines because a resonance increases the double bond character between the ring and the attached nitrogen atom. We now come to another functional group series, that is of the nitro compounds. The nitro group, that is the NO2 group, gives two strong bands in the infrared spectrum. In aliphatic nitro compounds, the asymmetric stretching vibration occurs in the range from 1600 to 1530 centimeter inverse, and the symmetric stretching band appears between 1390 to 1300 centimeter inverse. Now, for example, 1 nitrohexane absorbs at about 1500 centimeter inverse and 1380 centimeter inverse. Normally, its lower frequency band is less intense than its higher frequency band. In contrast with aliphatic nitro compounds, aromatic nitro compounds give two bands of nearly equal intensity. Conjugation of a nitro group with an aromatic ring shifts the band to lower frequencies, that is in the ranges of 1550 to 1490 centimeter inverse and 1355 to 1315 centimeter inverse. For example, considering nitrobenzene, that is aromatic benzene, absorbs strongly at 1525 centimeter inverse and 1350 centimeter inverse. Considering the nitroso group, that is Rn double bond O group, gives only one strong band that appears in the range from 1600 to 1500 centimeter inverse. You can clearly see the spectrum of 1-nitrohexane done in neat liquid in KBr plates in the following figure. Now students, we fall on to the category of next functional group series, that is nitriles, isocynates, imines and oximes. The C double bond N group in the nitrile group gives an intense sharp band in the region of 2280 to 2200 centimeter inverse. Aliphatic nitriles absorb at about 2250 centimeter inverse, whereas their aromatic counterparts absorb at lower frequencies near 2230 centimeter inverse. Aromatic nitriles absorb at lower frequencies with increased intensity because of conjugation of the triple bond with the ring. However, isocynates also give an sp hybridized carbon atom, that is RnCO, and hence give an absorption band in the region of about 2270 centimeter inverse, and these bands are broad and intense. An imine, that is RCH double bond NR gives a C double bond N absorption band in the region of 1690 to 1650 centimeter inverse. The intensity of the C double bond N varies in the intensity from compound to compound. An oxime, that is RCH double bond NOH, gives a C double bond N absorption in the range of 1690 to 1640 centimeter inverse and a broad OH absorption between 3650 and 2600 centimeter inverse. Now looking at the IR spectrum of butyronitrile and benzyl isocyanate, you can appreciate the difference between the series of compounds. Now these both are done in neat liquids and in KBr plates. Next we come on to the functional group series of carboxylic acid salts, amine salts, that is NH4 plus, RNH3 plus, R2NH2 plus, R3NH plus and amino acids. Now we look into details of their stretching frequency values. In carboxylic acid salts, the C double bond O stretching frequency appears little bit over value at lower frequencies, that is in the range of 1600 to 1400 centimeter inverse from the value found for the parent carboxylic acid due to partial carbon oxygen double bond character. Band due to asymmetric stretching, which is a strong band, occurs near 1600 centimeter inverse, while symmetric stretching, which is a strong band again, occurs near 1400 centimeter inverse. The amine salts show a NH stretching frequency in the range of 3300 to 2600 centimeter inverse as a broad band. The ammonium ion absorbs to the extreme left in this region, while the tertiary amine salt absorbs to the extreme right. Primary and secondary amine salts absorb in the middle of the range, that is between 3100 to 2700 centimeter inverse. The bending NH vibrations, which are again strong, occur at 1600 to 1500 centimeter inverse. Primary, which is the two bands, is asymmetric at 1600 centimeter inverse, symmetric at 1500 centimeter inverse. Secondary absorbs in the region of 1610 to 1550 centimeter inverse. Tertiary absorbs only weakly. All the amine salts show bands due to CN vibrations in the fingerprint region, but these bands are weaker. Amino acids exist as zwitterion and exhibit characteristic absorption due to carboxylate and primary amine salts. They show absorption bands of NH3 plus stretch, which are very broad, NH bending, that is asymmetric and symmetric, and C double bond O minus stretch, that is asymmetric and symmetric again. These are clearly shown in the figure, which is an IR spectrum of leucine. Now you can see the various stretching and asymmetric and symmetric stretching frequency values, and you can appreciate that for the amino acid, which is leucine over here. Summarize this module. The vibrational frequencies provide important structural information about a compound, and except for enantiomers, no two compounds will have the same vibrational frequencies. These characteristic peaks tell about the presence of some particular functional groups present in the molecule. This makes infrared spectroscopy a very simple and versatile tool for identification of unknown organic samples. We have described here the characteristic absorption frequencies of some functional groups like alkyl and aryl halides, alcohols and phenols, ethers and epoxides, carbonyl compounds like aldehydes and ketones, cyclic ketones, carboxylic acids, esters, cyclic esters, amides, cyclic amides, anhydrides and acid chlorides, amines, nitro compounds, nitriles, isocynates, imines and oximes, and also carboxylic acid salts and amine salts. I hope you found this module very informative, students.